So let's begin calculating the left-hand side, which is the double integral over the surface S of f dot over ds. Now remember, S is made up of three parts: the disk on top, where z equals 3, the cylinder itself, and the disk on the bottom, where z is equal to 0. So let's make a note. This is going to be the the double integral over S1 plus the integral over S2 plus the integral over S3. And start calculating those separately. Beginning with S1. So we want to parameterize this disk, and it looks like cylindrical coordinates is going to be an awesome choice of how to do it. So let's think x equals r cosine theta, y equals r sine theta, and z equals z. But remember, on this top surface, z is equal to 3. So that's all I have to substitute in, and that gives me parameterization. X equals r cosine theta, y equals r sine theta, and z equals 3. So the two parameters that I have left are r and theta, and phi of r and theta is r cosine theta, r sine theta, and 3. So remember, whenever you parameterize a surface, you have two parameters. Now the formula for big vector ds is going to be plus or minus the phi dr crossed with the phi d theta dr d theta. So let's calculate those two partial derivatives and then find their cross product. The phi dr is cosine theta, sine theta, and 0. The phi d theta is negative r sine theta, r cosine theta, and 0. So to take their cross product, I'm going to put ijk across the top and take the determinant of this 3 by 3 matrix. So the phi dr crossed with the phi d theta will be I times 0 minus 0 minus j times 0 minus 0 plus k times r cosine squared plus r sine squared, which is r. So to capture what we've got over here, I know that big vector ds is going to be plus or minus 0, 0, r dr d theta. Now a couple things to notice. One is that this is pointing parallel to the z-axis. And that's not surprising because this disk is perpendicular to the z-axis. So we expect our vector to be pointing straight up. Also, when we set up our bounds, we're going to have r positive, and I want the z component to be positive for this cross product. So that means I'm going to choose the positive of the positive and negative. So ds is going to be 0, 0, r dr d theta. And now we're ready to set up and carry out the integral. So we're looking for the double integral over S1 of f dot ds. And remember, f is 2x negative 2y z squared. Now 2x will be 2r cosine theta. Negative 2y is negative 2r sine theta. And z squared is 9. And that has to be dotted with the formula we got for ds, which was 0, 0, r dr d theta. Now remember, the radius of this disk is 1, so r goes from 0 to 1, and I'm going all the way around the z-axis, so theta is going from 0 to 2 pi. So let's carry out the dot product and then do the integral. So I have the double integral, 0 to 2 pi, 0 to 1, of 0 plus 0 plus 9r. Now if I want to, I can factor this as the integral from 0 to 2 pi d theta times the integral 0 to 1, 9r dr, which is 2 pi times 9 halves r squared, taken from 0 to 1, which is 2 pi times 9 halves, or 9 pi. So for S1, we're getting an integral equal to 9 pi. So let's capture that right here. And continue. Now instead of going to S2 next, let's go to S3 since it's so similar to S1. And we'll come back and do S2 in a minute. In fact, S3 is so similar to S1, it would be an excellent exercise for you to pause the video and see if you can figure it out. So the general cylindrical coordinates are x equals r cosine theta, y equals r sine theta, and z equals z. This bottom disk has equation z equals 0. So if I take that z equals 0 and substitute in, then I get my parameterization. My parameterization is x equals r cosine theta, y equals r sine theta, z equals 0. Or I can write phi of r and theta is r cosine theta, r sine theta, and 0. Now once again, let's take our partial derivatives and then find their cross product. The derivative of phi with respect to r is cosine theta, sine theta, and 0. The derivative with respect to theta is negative r sine theta, r cosine theta, and 0. And when I take the cross product, I get 0, 0, and then r cosine theta plus r sine theta, r cosine squared theta plus r sine squared theta is r. So ds, big vector ds, is plus or minus 0, 0, r dr d theta. This time though, notice that I want my vector to point straight down. So I want it to have a negative z component, which means that I need to choose the minus sign for ds. So let me record over here. The ds I use this time is negative 0, 0, r dr d theta. Or if I want to, I can multiply that negative sign inside and make this 0, 0, negative r dr d theta. And now we're ready to set up and evaluate the integral over S3. Once again, I'll remind us that F is the vector field 2x negative 2y z squared. X is r cosine theta, so I have 2r cosine theta. Y is r sine theta, so negative 2r sine theta. And z is 0, so that means that z squared is 0. And then I have to dot that with ds, which is 0, 0, negative r, dr d theta. Well, that's interesting. I know I haven't set up the bounds yet. But look, when I carry out the dot product, I get 0 plus 0 plus 0. So this is the double integral of 0, which is 0. So the integral over S3 is nothing. We don't get anything there. So in the next video, let's come back and figure out what the double integral over S2 is so that we can add the three partial results.